15, I want you to put a star by this problem. Star by this problem as well. Because this one is one that normally throws people off. Because if we look at trying to factor the denominators, we've got x plus 3, and we've got x, and we've got x plus 3. A lot of times students just want to say that the LCD is x plus 3. Why does that not work?
Because there's another x.
Because the x is its own factor. So just like we consider the monomial separately from the binomial factors, this x is its own thing as well. So LCD is x times x plus 3. There's our dynamite. Now, what about restrictions? What are the two things that x can't be? Huh?
How are there two things?
Because we have two different denominators. So on this one, only 3 for that x and 3 for that x would make it undefined. But what can I plug in for x to make this one undefined? -3. What about this one? 0. Because you can't divide by 0. So any variables that make your denominator 0, those are going to be your restrictions. Now, folks, on this problem, I'm going to show, it's not really a shortcut. We're still doing the same thing. It's just not writing out all of the work. Instead of rewriting out the whole thing, I'm just going to write the LCD dynamite up above. So I'm going to multiply that by the dynamite, this one by the dynamite, this one by the dynamite, making sure that I'm checking, are there any negatives that I need to distribute? No. But if you have a highlighter, there is one on number 16. There's one on number 1 as well. And I would say missing the negatives is one of the biggest mistakes on this part of the test. All right, folks, so I was just a little bit less clean with my work here, but the process is still the same. Folks, when I cross off those x plus 3's, what are we left with? X times x, or x squared. The x's cancel. We're left with 2 times x plus 3. Then the x plus 3's cancel. And we're left with x and -3. So, folks, what little red flag is going off in your brain? Or what little alert?
There's an x squared.
There's an x squared. Anytime we have a quadratic, we think factor, and before we factor, it's got to be equal to 0. So I'm going to, I'm going to distribute x squared plus 2x plus 6 equals -3x. I'm going to move the 3x over to the other side, so x squared plus 5x plus 6 equals 0, x plus 2, x plus 3. And so x equals -2 and x equals -3. Do we put boxes around both of those and say it's all good?
No, because you got check.
What's not all good? The -3 is extraneous because that is one of our restrictions. If I try plugging -3 back in, we end up dividing by 0 and it makes our fractions undefined. But -2, it's all good. Now, sometimes both solutions will work. Sometimes one solution will work. Sometimes none of them are going to work. So similar to the other places we've had extraneous solutions are you won't know until you plug back in how many solutions you are going to have.
Is there a way to know, like, how many solutions you will have?
No.
You just gotta check for extraneous.
Yep, you just got to check for the extraneous. But just be careful, folks, that you know x times x is x squared and not 2x, because that's kind of an easy place to go wrong in these problems as well. Great question. Any other questions on this page? Because I think we're ready to move to learning target number 3.
Let's do it.
All right, let's go. All right, so 7.1. This is a big one because the only instructions are to simplify, but as you probably remember from this chapter, there's lots of little nuances to these square root problems. First, when you simplify a square root with variable powers, you take power divided by the index, or you break the power. and we'll talk about breaking the power. You will also look for perfect square factors. You will be given the perfect square sheet to use on your finals, so you don't have to have that memorized. You will be able to use that on the test. So look for perfect squares, perfect cubes, perfect fourths, perfect fifths, etc. But always check for simplifying at the end. See if there's any more things you can do to simplify the radicals or simplify the expression. So folks, I think we're just going to do just like one of every type of problem. So let's go ahead and start with number 18. Ooh, I remember what else I wanted to write at the top of this page. Don't forget the index. Don't forget the index in your work. Don't forget the index in your final answer. So as I'm looking at number 18, what is our index? 4. That means when I go to simplify this, I want to find a perfect fourth factor of 48. So as I look at my happy little square sheet, we look in the perfect fourths column. Is 81 a factor of 48? Nope, it's too big. So it looks like our only option is 16. Is 16 a factor of 48? Yes. So I'm going to split this into 16, which is a perfect fourth, and 3, which is our non-perfect fourth factor. For the variables, power divided by index, 8 divided by 4, gives me v squared on the outside. Now, what about z to the 13th? Do I want to write z to the 13 halves? No. This is where we want to break the power. We want to break it down into the biggest thing that is divisible by 4 and whatever is left over. So what's smaller than 13 that's divisible by 4? 12. So 4th root of z12. There's the perfect one that's going to be divisible. And then what's left over is z to the first or just z. Notice that I'm putting that index of 4 in every single step of my work so that I don't forget it along the way and accidentally put the square root of 16, whereas I am looking for the 4th root of 16, which would be 2. So I've got 2 for the 4th root of 16. Bless you. I've got v squared. I've got power divided by index, z cubed. And then 4th root of z. So then, putting all my outside stuff together, 2v squared z cubed, and then the 4th root of 3z. So making sure we include the index with our final answer. And that's our simplified expression. Any questions on finding perfect factors, power divided by index, or breaking the power?
So if it's divisible by the index, you just divide it, but if it's not, then you have to
Break it into something that is, something that is, and then whatever it's left over. So just like we split 48 into the perfect and the non-perfect, we're doing the same with the z to the 13th. It's just we're dividing the index instead of looking for the perfect number. So let's go ahead, done 18. I want you to see what you can do with number 24 and number 30. So I'm going to give you a couple minutes to try number 24 and number 30. I'll give you 4 minutes to try those two.
It's more time to think. I switched it.
Switch it, and it doesn't matter what happens.
Basically, I dropped chemistry. I'll do that. Well, I'm not doing chemistry. I only need one science credit.
Oh,
So I'm taking geology next year. So
Cause like at this point, like she said, do you wanna take any of those tests? I'm just gonna take
they wouldn't go any good at me.
Okay, that's what I wanted to check. Yes. Yeah.
I can't even describe it.
Oh yeah, these are.
I don't even like remember where to start.
Well.
All right, folks, let's start talking through number 24. So first, that was only 2 minutes. That's fine. On number 24, the deal with adding and subtracting radicals is you can only add like radicands. So let's put a little note up at the top. For adding and subtracting, must have same radical. Adding and subtracting must have the same radical. So if you're looking at number 24 going, well, none of those radicals are the same, Mr. Cairo, so I guess we can't add and subtract them. What must we do first? We need to simplify those individual radicals first to see if we can make them have the same radical stuff. So looking at 810, what jumps out to me about this one is the 81. So I'm going to go ahead and take out a perfect square factor of 81, which leaves me with the non-perfect square factor of 10. Now 240, why would I not want to split that into 24 and 10? Neither of those are perfect squares. Now, if you're trying to figure out the biggest perfect square that you can take out, what I would normally do, especially since 240 is even, I would try dividing it by 4. That breaks it down to 60. I can divide 60 by 4 as well. And that leaves me with 15. Are there any perfect squares I can take out of 15? No. So if I can take 4 out and 4 out again, that means 16 should be the biggest perfect square that I can take out. And I'm going to verify that because sometimes students are like, 8's the biggest perfect square. 8's not a perfect square, so you do have to multiply those together. And we see that 240 divided by 16 is 15. So I know it's not very fun, but sometimes you will have to guess and check a little bit on your calculator to try to find those big perfect squares. So it looks like 16 is our biggest. And then 15 is what's left over. So what about 250? Any perfect squares jumping out at you? 25. So 25. And then 10. So now I simplify. Square root of 81 is 9. So 9 rad 10. Square root of 16 is 4. So 4 rad 15. And the square root of 25 is 5. And take note that there is a negative in front. So do we have any like terms that we can put together?
9 out of 10, negative 5 out of 10.
That's right. If I have 9 radical 10s and I subtract 5 radical 10s, how many radical 10s do we have?
4 radical 10.
4 radical 10. So nothing happens to the radical. It behaves like a unit, but you do add or subtract the coefficients. And then 4 rad 15, nothing happens with that one. So this is as simplified as that answer will go. Questions on adding and subtracting?
That's not bad as the other one, the first one we did.
Yeah, like it's really simplifying, adding and subtracting. Multiplying, we're gonna not do a multiplying problem because we kind of have to hit it in a division problem anyway. So folks, we're gonna go over number 30 together. What is our rule with division? It's not like we really divide radicals. We can't have any radicals in the denominator. So let's write down a couple more rules up at the top. For multiplying, you multiply the coefficients and multiply the radicals. So multiply coefficients, multiply radicals. For dividing, no radicals in the denominator. You must multiply by the conjugate or the radical times itself. And we're going to define a conjugate down below by going over number 30. So looking at number 30, what drives the problem is we've got a radical in the denominator. Not good. I can't just divide by radical 2 over radical 2 because of this negative 1 there that would keep distributing to the radical 2. So when I have a binomial, we have to multiply by the conjugate of the denominator. The conjugate is the same stuff, but with a different middle sign. And I multiply by that on both the top and the bottom since I'm really multiplying by 1. Stars by this, highlight this because this was one of the more frequently missed parts on this portion of this unit's test. Why do we need to use a different sign? Because when I FOIL this, oh yeah, they're binomials, we're going to have to FOIL, the outside and inside products end up canceling each other out. So we're going to go ahead and distribute on the top together, and then I'm going to have you guys FOIL on the bottom. So 6 times 3 radical 2. 18 rad 2. We multiply the coefficients together. The radical comes along for the ride. My outside term, 6 times 1 is 6. Now my inside terms, I have the 3, and then rad 2 times rad 2 is rad 4. Then rad 2 times 1, rad 2. Now, I'm going to have you guys try foiling on the bottom, but before we do that, is there any simplifying that I can do on the top? Well, the square root of 4 is 2, so 3 times 2 is 6. So if I've got 6 plus 6, I'm going to have 12. Then if I have 18 rad 2 plus 1 rad 2 or a rad 2, how many rad 2s is that? 19 rad 2. So what I want you to do is FOIL on the bottom and try to simplify. Go. Yes.
Do quickly.
Oh, dude, you're working so hard now. Like, you don't have to do all that work.
outside inside products cancel. Square root of 4 turns into a 2. So 9 times 2 is 18. 18 minus 1 is 17. Division distribution, yeah, it's not going to lead to anything friendly. So this is our final answer. So remembering the conjugate, that's very important. And then also taking your time with the foiling.
You multiply the radicals together?
Yep, so you multiply coefficients together, you multiply the radicals together. So that's why here, 3 times 3 is 9, and rad 2 times rad 2 gives us rad 4 there. I think that's it for the radicals. So do you guys want to wait on the last 2 learning targets until tomorrow and just use this time to work on what we've done today?
Yeah.
Okay, let's go ahead and call it a day then.